In this video, we're going to look at an introduction at some of the concepts involved when you get to the 3D modelling side of the Aspire programme. Firstly, let's talk about how we represent the 3D data. Essentially, what we are looking at is a grid of pixels, and each one of these pixels is at a different z height. The concept is exactly the same as the executive pin art toy, where you have the pins that you can push a 3D shape into them and see that represented by the different heights of the pins being pushed up. And the difference with Aspire is that we are using 1 million or more points, so we can represent much more complex and smooth forms. We don't actually see each individual location. And in the software, we refer to these points as pixels. And this really is the same terminology that you may have heard used when people describe the points or dots that make up a 2D computer image. This really is the same concept. The more dots you have, the better quality image you have. So in the software, the more pixels you have, the better quality model that you will have. The quality setting in the software is referred to as resolution. You define this when you start a new session in the job setup form under Modelling Resolution as highlighted here. By default, we're presented with 3 options for this. First is your standard resolution, so this is where we apply 1 million pixels over the surface of your entire work area. Then we have high resolution, this is 2 million pixels, and then we have very high resolution, and this is 4 million pixels over the surface of your entire work area. And so this really presents us with a trade-off, because the higher the settings mean that we'll get a better quality model. However, it may mean that there may be longer calculation times for some modelling and toolpathing operations, and so you just have to balance it out so it's appropriate for your type of work that you're doing and the computer hardware that you are running. Now, resolution does not affect 2D or 2.5D content. That's all down to the quality of the vectors that you have drawn and the settings that you use in the toolpaths. Now, there is more detailed technical information all about resolution on the FAQ section of the Vectric support site if you wanted to learn more. For people who are new to this concept, it can be a little difficult to understand, so let's have a look at some rules for success. So the first thing you want to do is you want to maximise the area of the job that the 3D part covers. So you don't want to have lots of space in your job that is irrelevant to what you are actually machining. So a good idea is to make the job size slightly larger than the part that you actually plan to toolpath. And the reason for this is that you want to leave enough border for your cutout tool to go around. And so we can see in the image here that we've got a 3D model of a horse, and the rectangle that surrounds that horse is our job size. Now what we don't want to do is make the job size the size of the table or the material, unless that's the size of the part that you're actually cutting. So let's have a look at the 2 examples that we've got here. At the top we have a horse's head that is 10 inches wide and it's positioned within a job space that is 12 inches wide, so it's just a little bit bigger than the part that I actually plan to cut. Now at the bottom here we have that same 10-inch horse, except this time we've placed it in a job size that is actually 4 foot by 8 foot. And if we look to the right, we can see the quality difference that it makes to both of those models. So at the top here, you can see that we've got a very high quality model, and that's because we're maximising the number of pixels or the number of points within this work area. And so the model can use that to get the definition. Now at the bottom over here, because we are covering such a large area, we're actually getting much fewer of those points underneath our model, and so we can see that we're really sacrificing the quality of the model if we do that. And so it's very important to maximise the area of the job the 3D area covers. And a good idea is to look at the part that you plan to toolpath and add an inch or a couple of centimetres around the part, assuming it's large enough to accommodate any cutout operations that you plan to do. And in some situations, you may want to rotate the parts to best fit the shape of the material in order for you to maximise the number of pixels being used. And this is something to think about if it appears that there is lots of white space. So once the part is set up, what is it that tells the software to push these pixels up to the different Z heights? Now we use a concept called components. Components are the words we use to refer to the 3D objects in the software. When we create these components, that's going to push up the pixel heights in the software, and by combining these together is how we get the overall finished object, where these are managed in the component tree on the Modelling tab as highlighted in the image on the right hand side. Now the result of all of these individual objects combined together is what gives us something that we refer to as the composite model. And so this could just be a single component on a level, or it could be like the example that we've got here where we have an assembly of many levels, groups and components. And this is what you see in the 3D view. The result of all of these components and their combined modes, how they're interacting with each other, is what gives us that finished part, and that's what we're going to machine. So how do we generate these components? Now there are a couple of ways to do this. So one way is that we could use the modelling tools in Aspire to create different types of shapes. Now the model making tools are available at the top section of the modelling tools, as highlighted in the image to the left, is where we'd go to create our components, where we could look at using the create shape tool, where we'd take a vector and we could build that into a round or angled or even a flat shape. We could look at using the two rail sweep and the extrude and weave tool to create swept shapes. We could look at using spin and turn to create spun or rotated shapes. We can also look at sculpting, whereby we can edit a shape as if it were virtual clay. We also have the create texture area tool that will enable us to create pattern components. And then we have the add zero plane that will just create a flat plane that has a height of 0. We also have the ability to create a model from an image, and this is good for generating component textures. An alternate way to building shapes from 2D data in the software is to go ahead and import an existing 3D model. This may be something that you've previously made in Aspire and saved out, or it could be a piece of 3D clip art that you've purchased or downloaded from the internet. Or it could be a 3D model created in another CAD program that you may want to bring in and finish, and then create the toolpaths to cut it out on your CNC. So by working through all of the other modelling tutorials, you'll learn how to use each of these functions, and how to use the 3D editing functions, and how to import and work with 3D data that's been created from external packages. Now when you're creating your job, what's your typical workflow? So the first thing you're going to do is define your job concept and gather your reference material. So maybe this is information from your customer, or it could be things that you just bring together to begin your design. Then you need to create good quality vectors. All 3D work will benefit from good quality vectors. Everything that you've learnt about the vectors so far will ultimately help you create good quality models, so the better the vectors, the better the model. And so with those vectors, you'll begin to build the basic components with the modelling tools. And as you build more shapes, you'll need to organise your components into sub-assemblies, whereby you'd look at levels and groups. You can adjust the order and the combined modes of these components to slowly build a more complex shape, and that's managed in the component tree. Now, as you're doing this, you may use some of the editing tools to start to smooth and blend the components together to get the shapes to interact with each other just the way that you want. As with any project, iterate through where you may make changes for improvement, until you get to the point where you have a part that's ready to machine, where you may want to apply some finishing touches, for instance sculpting or smoothing, and everything you need to do to get it machine ready. So now that we've got the 3D part in a state that's now ready to machine, we could start to think about creating the toolpaths to cut this out on our CNC. Now the most common approach to machining 3D parts is by using two different toolpaths. We're looking at the 3D roughing and the 3D finishing toolpaths. Now the 3D roughing toolpath removes the majority of the material around the part using a larger tool. Keeps it slightly away from the finished object to make sure that we've got some material left for the second type of toolpath, which is the 3D finishing toolpath, and this is what cuts the finished surface of the model using a smaller tool with a smaller step over. And so that step over is the distance between each pass that the tool makes. And so if we take a look at the images that we've got here, we can see at the top an example of theatre masks been roughed out using a 3D roughing toolpath. So it's hogged away a lot of the material ready for us to go in with a smaller tool where we'd apply a 3D finishing toolpath. And with that 3D finishing toolpath we'd use a very small step over, and we can see the actual preview of the toolpath itself in this image here. So you can see the lines are very close to each other, and then the result of this is the actual finished cutout, which you can see at the bottom there. And so the smaller the step over, the better quality the finish will be. The penalty for this is that it's going to take longer to cut it out. As well as doing 3D toolpaths, you may want to combine these with 2D and 2.5D toolpaths. For example, you may want to run a 2D profile to cut around your 3D part. There are some 2D and 2.5D toolpaths that can also be projected onto a 3D shape. For example, I may want to cut out a model of a banner, so I'd run my 3D toolpaths first, and then using a V-bit, I could project the text onto the model with the V-carve toolpath. In addition to creating a 3D model to output to a CNC, you may want to export the 3D model to import into another CAD program. You may also want to export it to a 3D printer where you could save the model as a mesh so that you can 3D print it. You may also want to export the 3D model as a 2D grayscale. Some lasers cut grayscales as a dimensional object. And so this concludes a quick overview of the general concepts behind modelling in Aspire and the typical workflow that we're going to use with it. Now if you want to do this sort of work, then we recommend watching all of the 3D modelling tutorials that we have available.